Welcome to the 24th lecture video for Physics 4A. In this second lecture this week, we go beyond the simple harmonic oscillator to demonstrate some of the things you might see in your upper division study of physics and engineering. We do not have any homework problems this week that require the concepts and methods introduced in this lecture, but I still recommend this lecture as a preview of things you will see in the upper division. The first segment demonstrates something called a coupled oscillator and its normal modes. At this point, it's just an interesting demo for illustrating something unexpected, at least the first time that happens. This demo can serve as an example of the superposition principle that we will talk more about next week, and there are quantum mechanical phenomena that are analogous to a coupled oscillator also. Then the rest of the lecture covers the damped Simple Harmonic Oscillator. That is an SHO where a damping term was introduced to its equation of motion in order to model the more realistic oscillators in which mechanical energy is not perfectly conserved. And then the driven and damped Simple Harmonic Oscillator, one where a periodically applied force drives the realistic oscillator. This is something that can be very complicated mathematically. So we are going to introduce some calculational tools that I believe are accessible at our level. Complex exponentials. You may remember them from your trigonometry class. In case not, I will start with a written resource you can refer to. This is it for this week's coverage of oscillators. Next week, we continue to waves and wave interference phenomena, where the concepts and terms we introduced this week will continue to be useful. So this is the demo I was talking about last time. So last Tuesday, we looked at oscillations, and you looked at simple harmonic oscillation with a spring, with mass on this spring, right? That's the demo that we have used for a while. So we introduced the oscillation with that because that's what you're familiar with. It's easier. But I want to use this setup to illustrate one thing and actually talk about one more thing in a little more detail. So this is an example of pendulum. You have actually seen pendulum before, right? And you see that this moves back and forth like in a, like tick-tock kind of regular way. The same way this mass was oscillating on the spring in a regular way. So you can imagine applying the mathematical description that we were applying to mass on a spring the exact same way to here. So this is another example of simple harmonic oscillator. If we had to give it a name, it would be pendulum. And we'll go through the derivation of this pendulum equation of motion so that we can see that the solution to this looks exactly like what we looked at on Tuesday. What this setup is for right now is to illustrate what's called coupled oscillators. So that's this demo that you saw before, right? Where it started out oscillating up and down, and then over time it's rotating that way. I prefer this demo because this is, one, easier to explain, and two, easier to manipulate. So let me demonstrate one of the features of this coupled oscillator with this demo. So this is how I'm going to set off this oscillation. I'm going to set it off so that only, let me give them a name, Alice and Bob, A and B. So I'm going to start this motion with only Alice moving. So I'm going to pull Alice back and let go. And as you watch this over a period of time, I want you to notice what happens. So Bob starts to move, and you will see that over time, Alice actually comes to a stop. There's a moment when she comes to a complete stop. Well, when it comes to, it's a mess. I know it's right here. Alice is at a complete stop. But it doesn't stay there. It actually gets moving again. And then over time,
Bob will come to a complete stop. Wow. I'll wait until Bob comes to a stop and then I'll continue. This does take a while because, yeah. So this is, wait, it hasn't come to a stop yet. I mean, you believe it'll come to a stop, right? Okay. So this is an example of coupled oscillator. And I will tell you right now that coupled oscillator as a topic, it's an upper division level topic. So other than doing this demo and giving you some terms to, I don't know, Google search, we won't really talk about it. But it's an upper division level topic to actually deal with it in detail. But we can handle it in a conceptual level. In a conceptual level, this is one way I can describe it. So I start by putting energy into A. And as A moves back and forth, what you are saying is that some of this energy transfers over to B. And then you wait long enough, that energy transfers back to A, back to B, back to A, and so on. If there was no friction, this would go on indefinitely. And so what do you think is the mechanism of energy transfer? Tikal?
How is it being transferred?
Yeah, so when I put energy into A, how is that energy that I'm putting into A getting transferred into energy of B?
It's moving the mechanism back and
Yeah.
forth.
Yeah, as you watch this, you realize that, notice that this support is moving back and forth, right? Yeah, you might have thought that's because I don't have proper budget to put a good support. But actually, the fact that the support moves, it's an important part of how this works. I haven't actually tried this, but let me try this. Let me actively stabilize it just by holding on to it. Can I do it? I don't think I can actually do it. So there's a reason this is a 2 kilogram mass. It's heavy enough so that it can actually shake the support. Now, let me show you a little bit of change from this. So they look the same length, all symmetric. I'm going to just change the setup here slightly by wrapping the string around this mass. I'm going to, by wrapping the string around this mass, and I'm trying to avoid it having like unwrapping and just tumbling down. Let's see. I don't know, it's a pretty heavy mass, and this paper clip is really flimsy. All right, I think that'll work. All right. So, all right. So let's try it again. I'm going to put energy into A. Let's see if that transfers over to B. So some of it does, right? But not quite. In fact, we can wait for 10 minutes, and not enough energy will really go into B. And since it's not going into B, it stays in A. So what do you think was the biggest difference between the setup we had before and the setup now? So this support, it's still shaking as this moves back and forth. So why is that energy not being transferred into this? Wait, what? So the length is different, but it has really nothing to do with the radius, nothing to do with the torque. Yeah. Asia, you're going to say something? Yeah, so the difference in height is different, but you know, the height is different. But I want to express it in a way that it's not specific to this pendulum setup, because the description that we are trying to give, it's something general that applies to all simple harmonic oscillators, whether it's based on pendulum motion, whether it's based on spring motion. Whether it's based on spring motion, this feature that we are going to describe will apply to all simple harmonic oscillators. So, let me show you. It's kind of hard to guess at this without having seen it. So you see how fast this is moving back and forth, right? Now watch. I'm gonna make this move by putting energy into B instead. Do you see a difference? What's different? Ali?
Energy didn't transfer to atoms.
Yeah, so it's not transferring. We know that already. But what is different in how A is moving and how B is moving? Yeah, this is faster. So this is one of the features of the simple harmonic oscillator that we looked at last time, and we didn't really spend enough time on it. That's why I want you to highlight it. So when you look at simple harmonic oscillator motion, there's really if you had to pick out the one thing that characterizes a simple harmonic oscillator motion, is that it has a natural frequency of oscillation. A simple harmonic oscillator motion has a natural frequency of oscillation. And you saw this with the mass on a spring system, right? We derived, so if when you describe the motion of the mass this way with this function, the height of the mass as a function of time is equal to some amplitude times cosine of omega t plus the phase factor. What you saw last time was that a lot of these parameters were variables or undetermined, except one. The angular frequency here was determined by the equation of motion. So for mass on spring, you saw that this omega was equal to square root of k over m, right? And this is the property of the system. It's a constant value. So if you have some mass that's hanging from a spring, then it naturally will oscillate at this particular frequency. And no amount of what I do, like if I try to make it oscillate, oops, too much. If I try to make it oscillate at a greater amplitude, that will not make it move at any faster frequency. I mean, it'll move at a faster speed, but the frequency will be the same. That's what you saw in the lab, right? So that feature transfers over to any other system that you would describe as a simple harmonic oscillator. So that's what you are seeing here. These two different pendulums, they have different parameters, different length. And that length somehow must go into the equation that determines its natural frequency of oscillation. And we'll take 20 minutes or so to look at that. So that's what you are seeing here. These two have different natural frequency of oscillation. So in terms of trying to transfer energy from A to B, as this moves, it shakes the support at a particular frequency. And the frequency that this is shaking the support at, it's mismatched with the frequency that this needs to gain a lot of, because you can actually imagine making this move with a very tiny amount of force. I think, can I do it with my breath? I might be able to. So I'm out of breath. If you do the correct frequency, you can do it with a very small amount of force. This is tied to something called resonance that we won't spend a lot of time, but that's the important part in how energy transfers from this to this. So the shaking of the support, it's very small. It doesn't cause anything to shake at a great amplitude, but when these two have the same length, so from the equations that we are going to go through in a little bit, these two happen to be oscillating at the same frequency. So that when I get one to move first, then this shakes the support, and it's shaking at just the right frequency that with each cycle, it's putting more energy, more and more energy into B. And I guess as it's doing that, so it's losing energy, so it slows down, comes to an eventual stop, and then at that moment this is shake. Wait a little bit. So at this moment, B is shaking the support, and the shaking of the support puts some of the energy back into the A. Good. So let me just finish this discussion with a coupled oscillator. So in upper division, they describe this in terms of normal modes. And one way you can actually describe it is this system as a whole has two different ways it can shake. That's the normal mode. So let me write down because for coupled oscillators, normal mode is the mode in which there's one single frequency of oscillation, and it's sort of not fixed. We call it stationary state sometimes. If you watch it, you will see it. So it has two normal modes. It's one normal mode is this one, where these two shake at the same, like in sync. Then it's you will see if you watch it for a while, you will see. Oops. I did not think that through. So this is the system fixed up. It's shorter than it was before. I think it still works. So let me just demonstrate that it still works. If you start the motion, then it does do that. Now, what I want to I'll wait until this stops so that you can see that it comes to a complete stop. And then as this continues to move, this now moves back and forth again. Good? So you're convinced that it still works. So this is the normal mode that I was trying to describe, but I could only gesture before. So this is the one normal mode that moves at a particular frequency. And you see, look at the motion of the support, how the support moves along with both the masses moving together. And this is the other normal mode. This has two normal modes. What you just saw was one, and this is the other normal mode. And look at how the support actually doesn't move as much because it's getting pulled and pushed the other way. So as a result of that, these two normal modes, these two stationary states, they have different frequency of oscillation. So what you are seeing here as this motion, you can describe it as sort of combination of those two normal modes happening at the same time somehow. And so when these two normal modes, this and this, when they're completely, when I sort of synchronize, imagine one starting this way and the other one this way. At time equals 0, it will look like this motion. And as this shakes back and forth, I guess normal mode that's going this way, it has a faster frequency. So that sort of starts going faster. Then at some point, it'll come to a combination that looks like this plus this. So that's when this is at rest and this is moving. And so all of this will make a little more sense once we've done something called the wave interference in the context of waves.
So what I want you to point out is I think what's gonna come up in chapters 21 and 22. And I think chapters 18, 19, 20 are also something that we've covered. Pretty sure when he does rotation in space, he'll talk about cross product. And all of that is really useful to read through. So again, I strongly recommend, for those of you who want to get a deeper understanding of mechanics and all these, coordinate system, formal stuff that I skip, that if you feel like all that material that I covered is too easy, whereas a slightly more challenging material, then this is what I would recommend. So with that, let me look at the material that I want you to point to, and maybe use the tools that he's going to introduce here to do some analysis of damped harmonic oscillator. So let me start out with the harmonic oscillator. So I'm gonna briefly just skip through the sections and just to highlight some of the key things. So when he covers this section, he'll cover it the exact same way we are, using trig functions, because he hasn't talked about complex exponentials here yet. He won't introduce those yet, but let's just briefly skim through how he covers it and match it up with how we cover it, which should mostly match up. I think if we do side by side with OpenStax, then they should mostly match up. So he talks about linear differential equations. And what he's gonna get to do is he's going to talk about, with a harmonic oscillator, the thing that's going to lead to complete description of the simple harmonic oscillator is what's called equation of motion. That's going to be in terms of a linear differential equation of up to some order n in terms of order of derivatives, but they're all going to be linear in the sense that you are not going to be multiplying x to itself, like there won't be x squared, there won't be dx dt times x, all these will be linear. So when you look at the harmonic oscillator and you analyze it using Newton's second law, let's see, simplest mechanical, upward displacement to x, and we also suppose spring is perfectly linear, which means it obeys Hooke's law, that you can describe the force with minus kx, minus sign indicating that it forces the opposite way from the displacement. And so skipping to thus mass times acceleration coming from Newton's second law must equal the net force, the spring force. So that's where he's starting. If you look at our textbook, we'll start with some qualitative description. We'll skip all that, which Feynman has skipped. And then he's going the textbook, once it's talking about equations of simple harmonic motion, then it'll talk about this displacement. Okay, that's the solution, which Feynman will build up to. Your textbook just throws it at you. Where's the equation of motion? There is this. No, this is not equations of motion. The equation of motion should be the thing that describes the physics of the thing. Is it not? Okay, where it talks about period and frequency of mass on a spring, and so this portion here, where it starts with the force, so force, mass times acceleration, so this equation is what Feynman has here. And this is something actually, it's quite common to see. A lot of classic textbooks in physics will skip a lot of the fluff up there that non-classic textbooks have. If you ever take upper division quantum mechanics and your instructor uses the textbook by David J. Griffith, Introduction to Quantum Mechanics, Griffith on page 1 starts with something called the Schrödinger equation, because he's assuming that people have seen all the introductory material in the lower division modern physics class. And there's a lot of simplicity there in starting with a key equation and building up from there all the other stuff that follows. So where this is like 2/3 of the way through the section, and that's where Feynman will start from. So he simplifies this, or I guess the way he does it is he redefines his unit system so that the ratio of k over m is 1. All right, that's fine. Just remember that when you are comparing your numerical result with anything. And then he then builds up from here. He's gonna, instead of trying to solve this directly, which will take higher level method than what first semester physics students might have, he guesses a solution, x cosine t. And in the unit system is working with, where k over m is equal to 1, this works fine. And you plug it in and see first derivative, second derivative, that satisfies your equation of motion. So, and then he works through the rest. And all this discussion, I do recommend that you read through it and reintroducing this constant and all that. And then he so this solution that you have, it's not the most general. So now he's expanding it, generalizing it to consider the situations where there might be a phase shift, and which your textbook also does, which your textbook just jumps to. Your textbook just throw this solution at you, or it threw it at you a few paragraphs above, so I prefer Feynman's approach. Start with where special case where phi is equal to 0, and then introduce phi, because phi phi doesn't have to be 0 for the solution to be valid. So he's starting here, and he's showing for, I think, does delta have to be small? I don't think it necessarily has to be small. Here he's using that trig identity that you will see us use in other contexts, but you use this to expand to see the most general solution would look like the sum of cosine and sine functions. Does your textbook do that? Your textbook might not do that. Yeah, your textbook doesn't do that. And it's the kind of, this is what I mean, going through the Feynman lectures will help you gain a deeper understanding of mechanics. Because your textbook never told you that when it tells you that this is the general solution, there's a different form you can write this in. You can write it in this form. This is also valid. What connect the requirements that both this form and this form satisfies is that there are two free parameters, an amplitude and something that connects to phase shift. And it's gonna be a combination of A and B that'll give you the amplitude and phase shift. And yeah. So anyways, so Feynman goes through the rest, and he connects the harmonic motion to circular motion, which your textbook does in a different section. I think I saw that when I was looking through, comparing simple harmonic motion to circular motion. Yeah, sure, it's a nice coincidence. I don't know how much utility there is, but read it through Feynman lecture. Whatever utility there is, he'll mention that. I don't know. I don't think I ever saw it that being useful. Initial conditions. Let's see. Yeah, and he talks through some of that energy in the simple harmonic motion, which your textbook covers in this section here. And I think he might not be covering. Okay, he covers a forced oscillation. And let's compare how Feynman covers it with your textbook section. Because handling this mathematically is pretty challenging, which is why when you look at your textbook won't even attempt to derive this. It'll just throw the solution at you. Here's the solution for the amplitude in terms of the driving force and the frequencies. Like it doesn't, it says it is left as exercise. I mean, yeah, you can do it. It'll just take maybe about a page of algebra and trigonometry. So that's what your textbook does. They have their reasons, and it's not invalid reason. Let's see how Feynman does it. He starts with the equation of motion. Same expression for force. Is it the same? For some reason, your textbook uses sine omega t. Alright, doesn't matter. In your textbook included this damping term. And yeah, so I guess B, if you just set B equal to 0, you would get the special case of where there's no damping. So I think it's fine. But let's look at it here. So so he has, with this special case, he proposes a special solution. And then, so he starts out with a simpler case, and I think this might be slightly easier, because you don't have to deal with those extra terms having to do with the phase shift. Now, this would have to be right-on phase, and can divide that. The answer to C must be, oh wait, I guess, does it not have to be the same frequency? I guess it doesn't have to be. Omega is very small. Only if we started that just right? Transient response, yeah. Also occur omega approach infinity, yeah. Okay, just this does the special case and doesn't do the thing that's more complicated. But this discussion is as it is, it's complete. It covers the kind of the key inside of the situation, which is that the phenomenon of resonance. That if the driving frequency is the same as the natural frequency, then you have a really high, really strong response to that small oscillatory driving force. So okay. As far as this section goes, it doesn't use the tool that I want to use to try to attempt a quick analysis of actually this exact situation. but where this is so complicated that your textbook has to just skip the details. I hope to actually go through the details. So the section you get to, let me go up, is where he introduces with the algebra. This is a really odd chapter title. Like he's been using calculus notations. This is calculus-based physics. What's this deal with the algebra? He's introducing something that sometimes gets really neglected in a math class. There are certain types of math that really physicists should teach it. And this Euler's formula is one such formula that really you should have a physicist to teach it, because this is something that should really have been covered in your trigonometry class. And I found that some instructors just skip it entirely because they consider it optional. Really, physicists should teach it. And this is Feynman, a physicist, teaching the basis for Euler's formula and how useful that is in describing oscillatory phenomena. So I'll just briefly step through some of the key equations, and I'll just make use of the result it drives. I encourage you to read through the chapter and get an understanding of it for yourself. So what is mathematics doing in physics chapter? Does he talk about how mathematicians don't teach it well? I don't know. Maybe not. Yeah. See here. Yeah. Oh wait. Oh, he's suggesting. Yeah, mathematics department should teach mechanics. Maybe, I don't know. Some cross training is fine. Anyways, starting. So read his whole story. So this is really a good grounding to start. It might look simple, but especially if you take advanced like upper division algebra, linear algebra, and sometimes called abstract algebra or group theory, it's built on this simple relationships like this. So it's worthwhile to kind of study and learn. And he's like walking through all this, a lot of which, as you are reading through, should sound like something you're familiar with. And then he will try to step through some of the things that one might try to do to abstract certain operations and generalize it beyond the domain and range that you are familiar with. So he's walking through all that with the kind of what does it mean to raise something to a rational power. And then I think he will probably talk about to real number as well, and approximating irrational numbers. Okay, you are still within the realm of real numbers, and he does some of these basic calculations to show what that looks like. Derive some rule, which actually comes from Taylor polynomial. But he doesn't use the word Taylor polynomial, I don't think. When I cover it, I use Taylor polynomial because I'm leaning rather heavily on your second semester calculus material. So all that, keep going. So he's developed all this, and now he's going to use what he developed here to talk about very small power of epsilon. And at some point he's going to this is you can say this comes from Taylor polynomial, or so keep going. Now he's gonna introduce complex numbers, and the introduction is same thing that you might have seen in your algebra class, college algebra class. Where does the imaginary number come from, in trying to find the root of this polynomial equation. And that gives you the property of what imaginary number I is. This gives you the algebraic rule that we can use to now try to expand some of the operations we had up there. So he's working on some of this algebra stuff. Okay, all good. And then now he's exploring the raising something to a complex power, applying the rules of algebra that he went over. You can separate out this way and look at this, and then this is going to be some complex number. Write it out this way, and he's going to write out a few things to try to justify the Euler's formula. So, goes through that, builds some table here, and then menu, let's see. Yeah, so read through it carefully for your own edification. And when you plot this out, this is what you will see. Sine for the imaginary component, and cosine for the real component. And so from all that, this is the Euler's formula. So this is the kind of from beginning to the end, the kind of introduction to Euler's formula and the complex exponentials. And what I hope he will say is the theory functions that are natural to geometry. Yeah. Does he mention the usefulness of that? Not quite yet. Let me look at the next chapter to see if he makes use of that. I think when he talks about resonance, there he will use the algebra that he developed to redo some of that analysis. So you can read through this. Just so that this isn't me just scrolling through Feynman Lectures, let me redo some of the analysis that your textbook does, just ourselves. So I'm going to try to solve this equation for damped simple harmonic oscillator using the complex versions of these real functions. So let's start here and kind of walk through this derivation of solution to driven damped simple harmonic oscillator. Maybe I should do damped one first. You know what? Let me do damped simple harmonic oscillator first, mainly because I see that I have 10 minutes and the driven part might make things a little bit complicated. One. Two, I know how to do the damped one, and even damped one, it's actually complicated enough that your textbook actually again just throws the solution at you. It doesn't walk you through the actual derivation of where does this come from, and it's a really simple process to do this if you make use of the complex exponentials. So we are gonna use complex exponentials, and with an invitation for you to read the Feynman lectures, the main thing I'm going to be using is the Euler's formula that says Euler's number raised to power I times theta is equal to cosine of theta plus I sine theta. Or if we have any oscillatory phenomena like e to the or if we have any oscillatory phenomena, like something that goes as cosine of omega t, then what we can do is we can represent that with e to the I times omega t, which will actually be this plus I sine of omega t. And if we want to get back to what the original real function was, all we have to do is take this and take the real part of that whole expression. So with that kind of implied promise at the back that we'll just take the real part, we're going to do all the algebra, all the difficult stuff using this complex exponential function, all the derivative and stuff. There are some care you need to take. You have to be really careful when you are multiplying or dividing. And at least for this derivation, you won't see me multiply or divide anything, because that's something you actually have to be careful about when you're using complex exponentials to represent the real functions. So, so we have this equation of motion. Let me write this up. M times the second time derivative of the position plus some damping factor times the first order time derivative position plus the term that comes from the restoring force. And when you look at the real solution here, that looks complicated enough that like I would never guess this as the solution, or it'll be really complicated to guess that. So let me start from here and let me give you the physicist's guess to any linear differential equation or maybe even nonlinear. So I'm gonna call this physicist guess to differential equations, which is exponentials. I'm going to guess that my solution to this, x as a function of time, is going to be an exponential function. More precisely, a complex exponential function. Now, I do have to be careful. If I simply say exponential of I times t, that actually has unit issues. This expression has unit issues here and here. One, whatever argument I put into exponential must be unitless. So for this time to just be standing there, that's not right. This says unit of seconds. So I'm gonna need some coefficient here. Let me call that b for now. And I'll figure out what that coefficient must be. And exponential of any just a number, it's just gonna remain a number. And here, this has unit of length or meter in SI units. So I need a coefficient here to make the overall units come out right. I called it an A. So with those, so this is going to be my guess to the differential equations. I'm a physicist, so I'm gonna guess a complex exponential might be my form of the solution to my differential equation. Let's see how right or wrong I am. Here's one reason why we guess a complex exponential. One reason is that the calculus is so easy when you are doing complex exponential. The first order time derivative, exponential, outside, nothing changes. So really, using chain rule, your only thing you have to worry about is making this factor come out. T is linear, so just a factor of I times b comes out. So the first order derivative is a times ib times exponential of ibt. Second order, which we might need, is going to be just this factor squared. So I squared will give me -1, so it'll be minus a times b squared exponential of ibt. So I have both of my time derivatives, so I can just plug this into the differential equation to see how the pieces fall out and what I can piece together from that. So I have m times my second order derivative minus ab squared, and I can see that all my terms here will have this exponential factor. So I'm just going to factor it out to the right, so I don't have to write it multiple times. So I have that, and there will be a big parenthesis for everything for this factored out exponential term. The plus b times a times I times capital B, okay, exponential being factored out to right, plus k times a, and then exponential term being factored out to the right. Let me write down the exponential term, ibt. So the thing that makes solving this equation simple is this, that in order for this whole thing to be 0 at all times, so this factor is not going to remain 0 for all times. There are some, well, actually there's, I think, no time when this whole complex thing is 0. So this is not 0, which means for this equation to work, the only way you can make it work is by making this term go to 0. So let me write that equation, and you will see beautiful simplification once I have written that equation. So I'm gonna write m times minus ab squared plus b times aib plus ka is equal to 0. Look at this expression and compare that with that expression there. This is a differential equation. This is algebraic equation. One of the magical things that complex exponential does in situations where they are appropriate is it turns a calculus problem into an algebra problem. So really all I needed to do from here on is do this algebra problem of figuring out what A and B are. So Okay, let's try to figure out what A and B are. I don't believe I have enough equations here. Let's see. Should I be able to figure out B? Possible. Yeah. I do have enough equations to figure out B, because here's this wonderful thing that's occurring, which is that every single term here has a factor of A. So I can cancel out A, because A presumably is not zero. If it's zero, then I have a trivial solution. So assuming A is not zero, I can cancel out all these factors of A that occurs in every term. So I have this equation here. Minus mb squared plus I lowercase b uppercase b plus k is equal to 0. Okay, so I have what looks like a quadratic equation in B. So, all right, let's work it out. So this is already in standard form. So what quadratic formula, assuming it works with complex roots. I think it does. I have to double check, but I think it does. Then what I can do is solve for B, which is going to be this thing. This is gonna. Let me rename some of my variables. The way I have my quadratic formula memorized this is gonna get really confusing. So everywhere I see B, I'm gonna replace with omega. That's what it's supposed to be anyway. Angular frequency of the oscillating thing. So, within the use of the quadratic formula, this coefficient here is the capital A, not to be confused with that A. This coefficient here is capital B, and this coefficient here is C. So what quadratic formula tells me is omega is minus B plus minus square root of B squared. Oh, good. That gets rid of I there. Great. 4AC, square root of all that, divided by 2A. That's what quadratic formula tells me. Let's plug in that expression and see what I get. Minus B, so it's minus I lowercase b plus minus square root of, great, so I squared, that gives me a minus sign, but no more. I was a little bit worried about having I under a square root. I don't have to worry about it. It's taken care of. There is a way to handle it, but I would have preferred not to. So minus, I see that minus sign coming in, so it's going to be plus 4 times A M times C K. Okay, take that and divide it by 2A. So minus 2M. Okay, interesting. So let's solve this out a little bit. I'm going to write this into a real part and an imaginary part. So the real part would be this term here. And let me observe a minus 2 or 2m into that there. So it'll be, minus plus square root of, let me write the positive term first. So this is going to become 4m squared. So it'll be k over m. I'm canceling out one factor of m squared with m, and 4 cancels out with that 4. So square root of k over m, and then minus b squared divided by 4m squared. So that's the real term, real, because sometimes it's not going to be real. And then I have my definitely imaginary term plus I b over m. So referring this omega back to the where it came from, it comes from here. It's omega is replacing b. So I can do that replacement here. So that b becomes what that omega was. Let me move this out to the right. So that whole complicated expression now falls into here. Square root of, minus plus. Yeah, it's fine. It could be either, it's a matter of phase factor. K over m minus b squared over 4m squared plus I b over, wait, did I forget a factor of 2? Yeah, I forgot a factor of 2. 2m. There's a parenthesis here, which means actually I get this thing. One of these factors will become real. So this I times that I will give me -1. So this is not one whole complex exponential. It actually includes, so let me write it out this way, a times. So let me write down the real part first. It's going to be I times I, so minus b over 2m times t. This is a real part. And then let me write the imaginary part. Minus plus I square root of k over m minus b squared over 4m squared times t. And using the exponential algebra rules, I can separate out these two terms. I can separate this out on its own and have this as it's a separate term. I can have a times the real exponential minus b over 2mt. This looks like some kind of exponential decay, and that is exactly this term here. That's the exponential decay term. I even got the coefficients right, which I swear I wasn't looking at when I was doing this. And then let me write out the complex exponential part. Exponential of minus plus I square root of k over m minus b squared over 4m squared, all of that, times t. And when you look at it, so it says cosine of omega t plus v. Let's look at just the solution for omega. When you look at solution for omega, that's exactly what we have here. This is the omega that they said it would be. So with identifying this as the omega, the frequency of oscillation, the solution we get here is exactly same as this solution here, the complex exponential version. And I did this in like 15 minutes, and I could have done faster if I didn't explain things. And so this is the beauty of using complex exponentials in calculation like this. What your textbook does with the real functions, it's gonna take a page of algebra to work it out. And you have to use some trig identities to reconcile all the expressions. But when you use complex exponential, the most complicated thing you have to use was this quadratic formula. That's it. And in a few lines of algebra, you get that. So anyways, so I want you to demonstrate that, and because this is material typically not covered in physics 4a, or at least this particular application isn't emphasized in the prerequisite material to physics 4a, I want you to give you the underlying material that you can read up on your own would be the Feynman Lectures, the chapters on the 21, 22, 23, that'll give you the written coverage of what I think is accessible to everyone in this class. And if you take physics 4b or 4c with me, you will see me cover this material again, where I'm better justified in bringing it in. But for this semester, I do strongly encourage people to check this out. It's a really powerful tool that really it doesn't take a lot to understand and make use of. Okay, so this is what we did last time with as an application of using complex exponentials that we introduced with the reference to Feynman Lectures. And last time we used this to look at damped oscillation, which your textbook covers, but without using complex exponentials. This is complicated enough that it just throws the solution at you. It doesn't even attempt to show that this is the solution because, even to plug it in with a product rule, it's a mess. It takes a page of algebra, so it doesn't do that. It just leaves you as an exercise. And I've shown you in a much shorter time that when you use complex exponential, that you can work through this much more quickly. Your calculus problem quickly becomes an algebra problem, and the algebra problem you have, it's just a simple quadratic formula, not that difficult to do. So that's what we did last time, and that was a kind of judgment call I had to make because we didn't have quite enough time to do what I was initially going to do, which was the driven damped simple harmonic oscillator. So your textbook does cover it. For some reason, I think they do it. Oh, yeah, forced oscillations. Good, they do it after damped oscillations. So your textbook talks about it, and I think they do give you the equation of motion. Yeah, here it is. So again, like with the last time, we are going to use complex exponentials under the assumption, I almost said pretense, under the assumption that you can take the real part at the end to get what would match with the textbook's treatment of these differential equations using real functions only. We are just going to use complex exponentials to get through the difficult part of calculus. And then once we are all done at the end, then we can always take the real part to get something that matches up with what textbook has. I almost said the pretense because we're not actually going to do that. We'll just leave it complex. But it is possible. In theory, it's possible for us to just take the real part. So we're going to take this equation of motion. You can, comparing this equation of motion for the damped simple harmonic oscillator, you can see what part they added. Let me first rewrite this in the form that they have first. So this was the equation of motion for just the damped simple harmonic oscillator. And I see that even though I copied this from textbook, in equation 15.27, they don't use this exact one. So let me first do a little bit of algebra to make that comparable. It looks like what they've done is first swap left-hand, right-hand side. So I'm going to write the term that's going to remain on the new right-hand side. That'll be second order derivative term, m times the double derivative x with respect to time. That remains on the side that they started with. And the other two terms, they get moved to the other side. And in doing that, they gain a minus sign. So let me move this first. That's minus kx. And then move this. That's minus b, the first order derivative. So that's the damped simple harmonic oscillator. And you've seen the outcomes of that. You kind of give an oscillator a kick, and it kind of, the oscillation dies down over time. So the new part that you are adding here to make it driven and damped simple harmonic oscillator is this driving term, plus. And then now, because we are using complex function, we'll have to make sure that this is complex. The way we are going to do that is the magnitude, amplitude of the force that we are driving. We'll say that's potentially a complex constant number. And then the function we use, it won't be sine omega t, it'll be e to the I omega t. Technically corresponds to cosine omega t when you take the real part, but here's the magic of using complex numbers. If this is like the real f naught times e to the I phi, then this multiplied to that will make it, sine of omega t or something like that. So by using e to the I omega t, we haven't really restricted anything. So this is the new equation of motion for driven and damped simple harmonic oscillator. So we're going to do the same thing that we did last time. So last time when we were doing damped simple harmonic oscillator, I gave you physicists guess to every differential equation, which doesn't always work, but it works often enough that it should be your first guess. Let me scroll down and get it. So this was a physicist to guess to differential equations, and I see no reason to change it. So it's going to be my same guess this time again. This has served us well last time. So why shouldn't we try it again this time? So we are going to guess an exponential, specifically a complex exponential, as a potential solution to this equation. And I should start labeling things carefully. So I'm gonna make sure that I remember that this omega here is going to be the omega of the driving force. In the last derivation, at some point I just did, oh yeah, this b is same as omega. I'm not gonna do that this time. I'm not gonna do that. although it might end up being that. We'll see. So we're going to use the same guess. So using this guess, we do the same thing that we do whenever we have a guess for a solution to a differential equation, and we are trying to see, is it a solution? We plug it in. So we are going to plug in our guess. So it's to that top equation that we are trying to plug it in. Let's do that. We have minus kx, that's that whole expression, a e to the I bt, minus b, the first derivative, and since the derivatives are even easy enough, I'm just going to do them as I go. When I take the derivative with exponential, I get nothing. I get the derivative from chain rule. I have to multiply by derivative of the inside, so I get a factor of ib coming out. So let me get factor of ib coming out from the chain rule times the original function that hasn't changed, I8 times e to the ibt, and we have just the driving force, I guess, plus f naught. I'm not gonna do the squiggly, but I'll just remember this is meant to be a complex coefficient, times the e to the I omega t is equal to m times, now it's double derivative, so two factors of this ib will come out. So it'll have to be I times b squared a e to the ibt. Oh, yeah. And I think this is yeah. So when an oscillator is forced with a periodic driving force, the motion may seem chaotic, and the motions of the oscillator is known as transients. Yeah, so there are gonna be transients. So let me just do a little bit of simplification here. So let me write the simplified equation first, and I will tell you what assumption that I'll make, and then go from there. So let me collect all the like terms. There are terms that depend on e to the ibt. Let me just collect all of them together. I guess I'm gonna put them all on the right hand side, and the remaining term I'll keep it on the left hand side. So we'll say f naught e to the I omega t is equal to, and of all the terms that I have on the right hand side, I'll factor out all the common terms. That's going to be a times e to the ibt. And let me write the remainder, minus k, took care of that, and then not minus, plus, it became plus when I moved them over, and then this also became plus when I moved them over, plus I times lowercase b times uppercase b, they're different, and from ib squared I get minus b squared, so minus m times b squared. Alright, let me do one more step of simplification, because I can kind of see that these two terms are similar in one way. They both depend on time. So I think I can gain some insight by combining those two terms. I can do that by dividing both sides by e to the ibt. E to the ibt. And from the exponential algebra rules, if I have e to the a divided by e to the b, that's e to the a times e to the minus b, and that's e to the a minus b. So from that I can see that the left hand side here will become f naught times e to the I omega minus capital B times t. That's going to be the combined left hand side, and the right hand side will now be, let me make some space for them. So e to the ib term is gone, a times plus k plus ib b minus mb squared. So from here on, we are going to make a simplifying assumption. Simplifying assumption being that what the textbook says, the motions of the oscillator in the chaotic motion, it's known as transient. So we are going to assume that we have weighted out the transient. If we have done that, what that means is this. A is constant with respect to time. And same thing actually with B. B is constant with respect to time. Because if they are not constant, then there might still be transients. There are still things changing with respect to time that has to do with the general properties of oscillation. A stands for the amplitude and B stands for the oscillation frequency. And I'm saying I want those to kind of settle down so that they have some stable amplitude and stable frequency. Now, once we assume that, then we see a constraint in this equation. You can see what things depend on time. On the left-hand side, this is constant, doesn't depend on time. But this t factor is here. This definitely depends on time. And on the right-hand side, nothing here explicitly depends on time. So if A is constant, and K from the equation of motion was already, it's a spring constant. B, the damping factor, that's also, we assume it's constant. And the capital B is constant, mass is constant. So the only way you can have this equation work where you are applying this assumption that A and B are constants is to have time dependence go away. Somehow you have to have it so that this expression is 0 for all time. And once you've said that, there's not 0 for all time. I guess, no. It's not 0 for all time, it's a constant for all time. And how do you make this time dependence go away? The only way to make the time dependence here go away is to say, well, that e to the I omega minus bt, that's e to the I 0 times t. When 0 is multiplied to time, then the time dependence is now gone. Any other choice of this coefficient where it's not 0, it won't work. This will have time dependence. And so this is the choice you are forced into. Despite what I said up above, I said up above saying, I'm not going to say B is equal to omega. Turns out it has to be. If you are saying that we have weighted out the transients and we are looking for stationary solution of some kind, then it must mean that B is equal to omega. So our original solution, let me copy that down. In some sense, we are getting a really boring answer because for this form of the solution that we assumed and are trying to fit how this could be a solution to our driven damped simple harmonic oscillator, we are saying the oscillation of that oscillator must be the same as the driving frequency. So it's kind of boring in the sense that we said we are driving this oscillator at this frequency, and in trying to look for stationary solution, we end up saying, the driving frequency is the oscillating frequency. But hopefully that makes intuitive sense. If you have some system that can oscillate and you're trying to move it back and forth at some fixed frequency, the frequency it'll move it's going to be the frequency you're trying to impose. So okay, that's kind of boring. So let's see if there's something more interesting we can find. We'll say, okay, our B is omega. So okay, let's apply that solution to this thing, and let's see what else we can say about this system. So if our B is omega, then it simplifies certain things. So on the right hand side, let's just rewrite this so that we have that expression written in now. Lowercase b times omega minus m omega squared. All right. And here now omega is not something to be solved for. It's something given to us. And this thing, it'll be e to the I 0 times t, which will be, e to the 0 That's 1. So this whole factor will just be 1. So we have this new equation that we didn't have before last time. It's an equation that gives you this amplitude A. Before, A was a kind of parameter that you would just set. Now we have a constraining equation for A. The driving force amplitude is equal to A times K plus IB omega minus M omega squared. Okay, so let me solve for A. Solving for A, that's equal to driving force divided by spring constant plus IB omega minus M omega squared. So I think you see a couple interesting things. One of which is this right hand side here. It looks like that's a complex number. So you have so F naught, even if F naught was, so let's say you write out F naught as with the explicit phase. So F naught times e to the I V naught. So so let's say for the numerator, whatever phase factor you have. You still have this phase factor in the denominator. So so the oscillating phase for A is not going to be the same as oscillating phase for the driving force. It'll be different. So I think what I should do is I should write out this complex number in the polar format so that I can do a little algebra with the phase factor. So I have this complex number, which let me collect the real parts together. That's K minus M omega squared, and I have an imaginary part, IB omega. So there's a way to, so in the complex plane, what this looks like is you have a real part here. I guess this could be positive or negative. Let's say omega is small enough that this will be positive. So at this point, that's K minus M omega squared. And then you have imaginary part. I guess this will always be positive. So somewhere up here, let's say here is IB omega. This is the imaginary axis. So this point, that's the Cartesian point that's represented by this complex number. So the geometric representation here is completely valid, completely something to be relied on. So this magnitude here, I can calculate it as magnitude of a vector with these two components. That's going to be square root of the x component squared plus the y component b squared omega squared squared, or sorry, that thing. Square root of that will be the absolute value of g. And as for the phase factor phi will be, so this angle phi here, the same geometric relationships that holds. Tangent of phi is the y component over the x component. B omega divided by k minus m omega squared. So, so we can write the amplitude A this way. We can say our amplitude A is, it's going to be the driving force divided by this factor here, square root of k minus m omega squared plus b squared omega squared. So I have this expression for A. So F naught divided by this absolute, this magnitude of that complex number, and the phase component. So I have the phase of the driving signal, I phi naught, and that's going to be divided by this. So this complex number in the polar coordinates, it's absolute value of g times e to the I, this phi. Yeah, I'm using different letter. So phi naught. So it's being divided by the number, so it's being multiplied by e to the minus I phi, where phi is given by arc tangent of this b omega over k minus m omega squared. So, all right, that's an expression. Let's see how that compares with the solutions your textbook gives. So, it has after some time, the steady state solution to differential equation is that. Okay. Oh, wow. So it gave a solution for A. Now watch, it's a solution for A with the solution we got. So F naught, okay, divided by, oh, we got that term. B squared omega squared, great. Now, looking in the left-hand side, you might think, oh, but this isn't equal to that. Are you sure? Let's see. So if you have k minus m omega squared, this is where you should think through how k relates with the natural frequency of oscillation. So we have this formula for natural frequency of oscillation. Omega naught is the square root of k over m for mass on a spring. Solving this for k, you have k is, so m moves over, m times omega naught squared. So where I have k, I could have really rewritten it as m omega naught squared. Same m. I can factor that out. So that's n squared there. And I have omega naught squared minus omega squared. Okay, their orders different, but we are squaring anyway, so the order doesn't matter. So, we got the formula for the amplitude, and it didn't take a lot of algebra. It didn't take a lot of calculus. It took, okay, it's, I guess, a page of algebra, but it's a small page of algebra. And I think your textbook never gave the phase shift. So, you know, they talk about the amplitude, and the one physical phenomena that your textbook doesn't get to, that you will see in physics 4b when we do driven AC circuit, because that has a situation that's really analogous to this. When you see that, what you will see is this is the formula for the phase of difference between your driving force and the response. So the surprising thing that you will see is that even though so for example, when you look at this, you know, so I think on resonance, where, so when you have omega is equal to omega naught, by which you mean square root of k over m, you can see that in this phase factor formula, when omega is equal to square root of k over m, then you can see that tangent of phi is going to infinity, by which we mean, since, wait, is that right? Is it going to infinity? I might have done something wrong. Let me think this through. I was expecting tangent of phi to go to 0. Phase offset between the driving force and the response of pi over 2. I'm not sure if that entirely makes sense. That's what the method suggests. For some reason, I was expecting, just having this plot of the amplitude as a function of driving frequency, I was expecting on resonance to have phi equal to 0, to have response that's completely in phase with the of the driving force. But the math above is suggesting not this, but suggesting that phi is equal to pi over 4, 90 degrees, which could make sense in some context. I'll have to think through if that's right. But at least so in your textbook, they only work out the amplitude. And we got the same formula, we got the same amplitude, and it in the process of getting that, they had to just throw away the phase information. And what you can see with the approach using complex numbers, you do retain the phase information, and there's the question of making sense of that, and I'll do that sometime later. So I might have to look at some numerical examples to see if this phase difference of 90 degrees is actually correct. But you got something to mull over, something to wonder, is that correct? And if it's correct, then you are gaining some the physical insight. And if that's not correct, then we'll find something that I did wrong above and correct those. So this is the demonstration of the working driven and damped simple harmonic oscillator using complex exponentials. Again, complex exponentials make mathematical problems like these tractable, solvable at our level. Because the main strength of this physicists guess to differential equations, complex exponentials, is that it turns the calculus problem into algebra problem. So, I have this simple algebra from here. And I did have to enter in the assumption of having weighted out the transients. But once you do that, then you see the constraint. You see what these parameters must be. And we got a formula for the amplitude that at least the absolute value does give me the correct answer. And it's one that agrees with the textbook answer. And it's much more tractable than the approach it would have taken if we were using this real trigonometric function. So what I thought would be good to do is do this numerically, and we can see if just my intuition was just in the wrong place, or if I did actually make a mistake in trying to do this analytically. We'll see. I actually haven't done this before, so however way it comes out, it'll be total surprise to me, so, as well as probably to you. So what I'm going to use for this exercise is actually something I have already done a demo of before. So one different way I can do is I can actually use the equation of motion that I wrote down for this particular system, the one using complex exponential for the driving force. So we'll do it that way. And we can also demonstrate some of the things that, before I was pretending to do and then never ended up doing, we can actually now do. So let me actually start a new page for this. So now I don't do this often enough that I forget a lot of what I taught myself when I was doing that other demo before, but let me try to remember. So first I need to define the variables I'm going to be using. So x is a built-in variable, but let me declare it anyway. Doesn't hurt anything. And I guess, let's see, do I want to keep it a k? Let me actually not keep it a k, because at the end of last week's session, I did work out an expression for the k in terms of the natural frequency of oscillation. So we'll use that. That'll help keep the units a little bit simpler. So the natural frequency of oscillation is given by square root of k over m. So in terms of this and the mass, k is equal to mass times natural frequency of oscillation squared. So we'll be using that symbol instead of k. So omega naught. B, damping factor, we still need that. T for time, and F naught for amplitude of the driving force, omega for the frequency of driving force. I still need the mass, and I think that's everything. And if I forgot something, I can do that again. And I want to define x as a function. Think this is how you do it. Let me see. Okay, yeah, x is a function of time, great. So now we can write down our equation of motion. The equation of motion is minus, so instead of k, I'm going to use m times omega naught squared times x as a function of time minus b times the derivative of x with respect to time, first order, plus the amplitude of the driving force. And I'm now going to use the complex exponential. Instead of using the the driving force expression that your textbook had. I will just keep with the complex exponentials. Exponential of, I think I is the right, let me see. Let's see, I squared. Yeah, okay, I is the right symbol for imaginary number in this system. I times the driving frequency times time. That's equal to mass times second order derivative of position as a function of time. So I think that's a correct expression. Let's see. Yeah, that's my differential equation. So when we are doing this with a computer algebra system, I came up with a guess that I plugged in. Now we don't have to. We have a proper computer algebra system. We can solve this ordinary differential equation. Think the function I need to use is something called the dsolve. Let me just double check, because again, I don't do this often enough. I forget this by the time I need to do it again. Yeah, so the first argument is differential equation, and I need the dependent variable, that's my x, and the initial conditions. Let me just type this in. So my solution will be dsolve differential equation, that's my equation of motion, dependent variable, that's x. Initial conditions are, I think I do want to specify them. So for the second order equation, okay, I'm specifying initial x. Let's say it's starting at 0 position. Initial, x is actually t, 0 time, 0 position. And then first order derivative, let's say it's starting out at rest. So that, it's a kind of the ordinary situation where you have a system at rest, you apply a driving force, and that, it drives everything else from there. Okay, that's the initial conditions. Independent variable, that's gonna be t. I think that's everything. Let's see what it'll do if I do this. So it should give me a complex solution, if it does give me a solution. Let's see, what is it? I think I need to, give it some, so it wants me to tell it, how some of the parameters work out, because the kind of the solution regime that you will be in will depend on the situation. So let's say, so example of legal syntax is that all right? We'll just use it, because I think this quantity will be positive if your damping factor is small, and that kind of sounds like what I want. So let me do that assumed thing. Let's see if that'll be enough. Solve again. It has to go through a few of these. Now so me being a human being would have assumed, of course that's a positive, what are you talking about? But the computer algebra system being computer algebra system, it doesn't know the physical meaning of mass and all these symbols, so all this could potentially be a complex number for it knows. So I do need to say that this is positive. All right, see, okay, it got me a solution. So this solution should now be a complex expression. So I'm not going to be dealing with this, in this algebraic form. This is one of the few situations where I would say, okay, just plug in the numbers, don't work with the algebraic expression. So let me substitute in some of the quantities. So I'm going to say my omega naught is equal to 1. So I'm going to be working in a special unit system where my natural frequency of oscillation is 1 in this unique unit system. And let me say my mass is also 1. And I think this, having fixed the natural frequency of oscillation, setting the mass basically sets what the spring constant of the system is. And because I want this assumption to be true, let's say B is some small number, 0.01 in this unit system. So that should simplify a bit. There are still some symbols left. Let's see. We have F naught and omega. Oh wow, omega to the 34th power. I have no idea what it's doing. All right. So let's say F naught is some small number, 0.1, because in most situations with the driven and damped simple harmonic oscillator, the driving force is usually small, and when you're on resonance, you'll build up amplitude from over many cycles. So, all right, let's see. Put in F naught. And I think if the only thing it depends on now is omega and time, then we'll be good. So there's t there. Let's try plugging in omega and just let's see, omega of 0, which is not a which is completely weird frequency to be driving it at. Okay, yeah, time is the only thing. So omega 0.1, yeah. Okay, so with this, now we can do the thing that before we are pretending that we would do and we never ended up doing. So before, when we were working with this analytical method, so when I put in this complex driving force expression, what I promised was that whenever we want actual result, we'll put this through a real part. And I even insinuated that I was just pretending to do it and I would never do it, and I never did it that day. But today, because so we're going to be wanting to plot this function as a function of time to look at the behavior of the system under this scenario. Now, the challenge in doing that, so for example, I can try plotting it now. If I try to plot it now, which I don't know the syntax for plot function, plot, yeah, I think it's gonna be plot this function and then t from, let's say, 0 to 100. Bell to evaluate function at, yeah. Because this is a complex number, 2 parameters, you can't really plot it with a single plot. So let me just go with what I promised at the beginning of the other time and just take the real part, because that was what we were always planning on doing when we expressed our driving force as a complex function. The promise from the beginning was if we ever need the actual values, the real number values, we can just take the real part, and the mathematical operations we've done will have taken care. Will have been careful so that when we just take the real part, it's mathematically sound. Mainly what that means is I made sure I didn't multiply two complex functions together. That's the one thing you can't do when you are working with complex exponentials to handle oscillatory phenomena. So, okay, we see something that, all right, it doesn't look like a simple harmonic oscillator, and I think I have a guess why. So this is our natural frequency of oscillation. We are really far from resonance. So it makes sense to me that this is oscillating relatively, and yeah, this larger, the longer period oscillation, that's my driving force. And this smaller oscillation is my natural frequency of oscillation. I think that's how it makes sense. Let me move this to 0.2 and see what we get. Okay, it's getting more interesting. I think my driving force is too big. Let me make it smaller. So yeah, we are still way off resonance, so our amplitude is pretty small. Let me get closer to resonance, 0.8. It's 0.2 away from resonance. Now it's a 0.02. Okay, let me go to 0.9. Okay, 0.04, it's double. Now when I'm at when I'm at 1, oh, we can double check the formula that was in the textbook and the one we derived last time. So this is right now on resonance. So the amplitude we get, 1, apparently, that should match what we are expecting from our amplitude formula. So our driving force is 0.01, and this is 0 because we are on resonance, and B is 0.01 squared, so 10 to the minus 4 times 1, okay, so under the square root it's 10 to the minus 4, so after square root it's 10 to the minus 2, 10 to the minus 2 dividing 0.01, that's 1, yeah, so it's just I don't know, conspiracy of numbers. It's not always going to be 1 like this. Like if this was 0.05, then you know, it would be that. So, but it is, I guess it is linear in driving force amplitude. So okay, that's fun. Now that's not the main thing that I wanted to do this for. So, you know, we can play with this like forever. There isn't really an ending point at which we would end. So we have the solution that we can plot, and what I want you to overlay on top of this plot is our driving force. So we can think the way to do this, do it as a list, and so my driving force will be F naught times exponential of I omega t, and we'll substitute use the same substitution function here. Substitute in all these. Some of these are redundant, or let me get rid of the redundant ones. I don't need omega naught, M or B. So, and I still need to take the real part only. And let's see what that plot looks like. Because the main thing I want you to, main thing I want you to do here is I want you to see if our driving force, which is in green, is going to be, and let me make it be smaller. Oops. Sorry, I made the B larger. Why is this? Okay, this doesn't. This is a little bit weird. Let me see. Did I specify B wrong? So in the equation back up there, I had a minus kx minus p times. It's running into some issue whenever I think I don't know. It might be some numerical calculation thing, like so up to point, and this is much larger than it's supposed to be, like compared to this. So there might be some singularity somewhere. I don't know. I'm gonna just stay away from those and stay around like between 0.1 to where the value I get is reasonable. That's what I was expecting. And 0.01, again, what I was expecting. And 0.05, what I was expecting, around the 0.2. Okay, that's all good. So we'll just stay there. And we'll just make the force so that it's comparable. We'll make it, we'll multiply this number by 10. I think that'll, or by 20. And we'll stay around here. And what I want you to check was back to our original question of what was confusing me about this phase factor, is if it's true that the phase is actually out of phase, which it might be. So let's see. We'll plot from, let's say, 12.5 to like 25. So 12.5 to 25. I think that'll catch a few cycles. Or 14, 15, 13. Okay, I can plot it from 13. So we are starting at what is basically, the sine wave. And this does look like something that's about 90 degrees out of phase. Not exactly, but close. So let's just test out this formula. So if this formula for tangent phi is correct, then as omega goes to 0, tangent phi should go to 0. So at very small, oh wait, so I think I do have to keep changing this. So if my driving frequency is really small, like 0.1, then the response x of t and the driving force should be more or less is in sync. And let's see. So 0 to 100. Okay, and I think these are the transients. So let me plot it from like 100 and on, 100 to 200. Then yeah, the transients have died away, and the response is now just, so let me stop multiplying this by 20. Response is, or not at all. Well, I do need them to be a little bit different so that we can tell them apart. But they are basically in sync. They are moving at the same. So when the driving force goes up, the response goes up. When driving force goes down, the response goes down. And if we move this out to from 1,000 to 1,100, then those small oscillations, the transients have died away, and this is just following the driving response. Exactly what we want, exactly what we would predict. Good. So okay, let's make omega something in between, like maybe omega of half of the resonance frequency. Then these should start to go a little bit out of phase. Let's see. And oh, it might be on some kind of resonance. Let me not make the let me stay away from the integer differences. 0.4 maybe. It's doing something weird. By weird I mean it's oh wait, I know why. I should have changed both numbers. Okay, so let's go back to long enough time later so that the transients have died out, and they are still right in phase. And I don't think that's what I wanted to see. Omega being so if omega is 0.4, yeah, it shouldn't be 0. Oh, but there's this factor b. I think I've forgotten about that. So let me do a slight bit of a rewrite. So tangent phi is equal to, I want to rewrite k in terms of the natural frequency. Then it'll be m omega naught squared minus omega squared b times omega. So think away from where this is equal to that, I can treat the denominator as constant of a sort, and the numerator will, so with b being small, so there will be a limit to how far off resonance it can go, because so how out of sync they can get, because the maximum for phi will be basically dictated by that b. So so let me let me actually calculate the numerical value here of tangent phi. So right now my B is 0.05 times omega 0.4, or let me write it this way. B times omega, I have the symbols. M times omega naught, or omega naught squared minus omega squared. So substitute in B is equal to 0.05, omega is equal to 0.4, omega naught is 1, and M is equal to 1. So yeah, so if that's a tangent phi, then arc tangent of that multiply by 180 degree time divided by pi. Yeah, only 1.36 degrees. No wonder I can't quite see it there. So I think the way to do it would be to so if I make, so let's just so anywhere below the resonance frequency, they will be kind of in the same phase. Like I can go up to 0.9, and it'll still be the case that they'll be kind of in sync, because it'll still be the case that they are in sync, more or less, because of that small b. So here, if I put in, I think I can begin to see the difference a little bit. So with omega of 0.9, the angular difference 13.3 degrees, and I can convince myself into believing, that's a 13.3 degree difference in phase between these two oscillatory phenomena. So what I was really interested in seeing is what happens as this approaches resonance. What my analytical expression claims is that as it approaches resonance, like right on resonance, this should approach infinity, positive infinity. So, so tangent, the angle should approach 90 degrees. Let's give it a try. So 9.5. And I think I can just leave it here. This is a good view. Maybe a little bit less, and multiply force by some factor. I don't know, 3 or 4, so that it can kind of keep up. It's beginning to get out of phase more and more. Let me put it to 9.9, and right exactly on resonance, what does actually happen is they are 90 degrees out of phase. And what you see here will be look a little bit different from if I plotted this from 0 to 30, I think. Because 0 to 30, the kind of the shape you see here, it's a little bit different. Because here right now you have a little bit of transients. So when you've gone out to 1,000 seconds, 1,000 and 2030. So here is where you've waited long enough, all the transients have died out, and the only thing you have remaining is, was it always that small? Sorry, 1 second. This response feels small. No, I guess that's right. 0.2 is, I think that is the right value with damping factor of 0.05. Yeah, okay. Just confusing myself. Yeah, so when you've weighted out the transients, then what you see here is right. So on resonance, your response is 90 degrees out of phase with your driving force. It's not something that I would have expected, but calculation shows that's right. So who am I to say that's wrong? And now once you go over the resonance, something interesting does happen. I think it's going to now go out of phase. So like if I'm at 0.01 driving, then because I'm now noticing that denominator will be negative. So with a negative denominator, this will give you something that's out of phase. So you can see this going past the 90-degree phase, and now it's at something like this. Then yeah, it's beginning to be out of phase, as in when the force is at maximum, your response is actually at the other extreme. And let's say you are out of at the higher frequency at 1.1, like 10% over the resonance frequency, then what the math would have said is, because your B is so small. So let me put the numbers in here. So because your B is so small, when your omega is 1.1, it would minus 14.6. Yeah, I guess I can imagine that. Yeah. So yeah, you have an issue because you're trying to get so I can't do arctangent anymore because the angle value is actually it's in the second quadrant. So doing arctangent won't give me the right number. So what I can do is yeah, I don't think I can even multiply this 180 divided by pi, because if I do that, yeah, it'll just give me that. So if you recognize that this is in the second quadrant, positive sign, negative cosine, then what you can do is to do 180 degree plus the 180 divided by pi times arctangent of that. So you have to do a bunch of conversions. So 165 degrees with all the corrections. That's at 1.1. Now, if you're a little bit farther away, then it should be close to now 180 degrees. So a little bit farther away at 1.3, pretty close to 180 degrees. That 5-degree difference you probably can't visually see, but that makes sense to me. And I do think I remember this from upper division classical mechanics, that when you have a driven oscillator, that there's a certain shift in behavior that occurs around the resonance, that when you are driving above the resonance frequency, then the oscillation is at like this. Now that I see it numerically, it doesn't sound surprising, but it's the kind of thing that you actually have to drive. I think most of us wouldn't have intuitive feel for how a driven oscillator behaves. It's one of the interesting setup where it does things that you wouldn't always expect. I guess I can do this because this is done in SageMath. I can actually redo this in real function really quickly. So I can take this and replace it with its real version, which is cosine of omega times t. I can just do that. And let's see what it'll do. So I shouldn't be giving it complex initial conditions. Okay, it solved something. Let's look at first the solution itself. At time equals 0, yeah, all the parameters where it should be 0. Okay, gave me 0. And let's take the derivative with respect to t. Okay, that matches the initial condition. All right, that's doing what it was supposed to. So, so let's just replot the things that we were plotting before. So we'll change this to cosine of omega t, and we don't have to take real part anymore because we've given up and gone to real functions. Let's see if that's any better. So SageMath might be doing something when it's a complex function that it shouldn't be doing, maybe. Now, what I can show, I think, is that all the results that we were looking at, they still remain valid. So, for example, if my omega is like So let's say on resonance. So this is where we are getting amplitude of 1. We still should get amplitude of 1, but now we are getting a better time behavior. So it's a slowly building up amplitude over time, which is totally what I would have expected, that our complex version just didn't. I don't know why. It might have been doing something weird with the time. Sometimes it does that. So yeah, good. It's building up to 1.0 amplitude over some time. And let me see if now that weird behavior with the damping factor is gone. So when I decrease the damping factor by factor of 10, yeah, this is probably still building up. So let me go to 10,000. Yeah, when it builds up the amplitude, builds up to 10, great. And when my damping factor is like 10 times less, then yeah, this is probably still building amplitude, so I need a longer amount of time to let it settle. And yeah, this looks totally as what you would expect. So I gotta research more why SageMath, when it's solving complex ODE, it does weird stuff. But none of the results that we talked about needs to change, because I just verify. And I guess in the spirit of verifying, I can verify the thing that was the most interesting thing, meaning so that right on resonance, yeah, it's 90 degrees out of phase, and when it's a little bit below resonance, like 0.8, then it's more or less in phase, and when it's a little bit over resonance, then it's completely out of phase, 180 degrees out of phase. Yeah, that result still holds whether you solve it with the real functions or complex functions. So that, at least that result we can still rely on, which you would have guessed. That's what we had with the analytical expression that we derived using complex exponentials.